Okay, so today's lesson is going to be on multiplying and dividing rational expressions. I'm not going to waste much time. We're just going to get started. Here we go. So today's plan is we're going to, well, first of all, last class, you learned how to identify non-permissible values, that's NPVs, as well as how to simplify rational expressions. This just involved, of course, factoring the top and the bottom, and then crossing off whatever factors appear on both the top and the bottom. Now we're going to build on that today. The focus instead will be on multiplying and dividing separate rational expressions and then simplifying them. So imagine you'll have two different fractions with polynomials on the top and the bottom. We're going to have to know how to multiply those together and then simplify them. It's really not much different than what we did yesterday. There's just kind of the added step of multiplying and dividing. You'll see what I mean when we get going. However, before we start, we're going to start by covering a weird factoring tip called additive inverses. It was something we didn't talk about last class. Let's get going. So in additive inverses, I want you to first consider x minus 1 and 1 minus x, obviously just backwards to one another, right? Now, clearly, these aren't the same. They're pretty close, but they're not the same since order matters with such subtraction, right? So if, let's say, x was 4, you would see that 4 minus 1 would equal 3. So for that first one, we'd have 3. And then 1 minus 4 in the other one, we'd have negative 3. You might already see where the connection is here, but again, they're not the same thing. First of all, let's look at how we could simplify it if it was a rational expression, x minus 1 over 1 minus x. Well, first of all, of course, you'd be tempted to just go, oh, x's cancel out and 1's cancel out. But unfortunately, that's not how rational expressions work, so we can't do it that way. Instead, I want you to consider this. We're going to leave x minus 1 on the top alone. X minus 1, nothing wrong with that. On the bottom, though, I want to write it so x is actually listed first. This would have negative x because of the minus x there. And then we'd have plus 1 because that's, well, a positive 1. Now, these aren't the same still, but there is something I can do that's going to make them look the same. Notice on the bottom, because this negative is sitting in front of the x right in front, we could actually factor out a negative 1. It's a little bit wonky, but let me show you. Again, x minus 1 on the top is going to stay the same. If we factor a negative 1 out of the bottom, you're going to see we have negative 1 come out in front. Negative 1 taken out of negative x is just going to give us positive x. And then if we divide positive 1 by negative 1, like factoring out a negative 1 there, positive 1 divided by negative 1 is actually going to be negative 1. So if this negative 1 was to bounce back through those brackets, we would have negative x plus 1. Notice now we have x minus 1 on both the top and the bottom. Those can now cancel out. So even though they weren't the same in the first place, we were able to just do one little thing to it to make it look pretty similar. Anyway, x minus 1 is going to cancel off the top and the bottom. All we're going to be left with is 1 divided by negative 1, which of course is just negative 1. The moral of the story is, if you have additive inverses, in other words, if you have something like x minus 1 and then 1 minus x, just the reverse of one another, they actually do cancel each other out, but you have to replace it with a negative 1. You could put the negative 1 on the top, you could put the negative 1 on the bottom. It really doesn't make a difference. Just understand that if you were ever to have an additive inverse like this, they will cross out. You just got to stick a negative 1 in somewhere, just so it balances out. Anyway, that does come up every now and then. Hopefully we'll see an example like that today. But if not, just keep it in the back of your mind. Okay, so we're going to simplify and list the NPVs for the following rational expressions. We're going to do these together, but I want you to think before I do them, what kind of factoring strategy we'll want to use for each one. Let's first investigate this first one here. Just take a look at it for a second. Look at the top and look at the bottom. Think about how we'll factor the top and think about how we'll factor the bottom. I'm going to start with the top here. You might want to follow along. 49 minus x squared. That doesn't look like most polynomials we deal with, but that is actually technically a difference of squares. Difference of squares are kind of funny. Remember, to factor a difference of squares, you just need to square root the first piece and square root the second piece and multiply by the conjugate of one another. In plain English, what that means is the square root of 49 is going to be 7 minus the square root of x squared is just x multiplied by its conjugate. In other words, if it was minus, now it needs to be a plus, right? So the conjugate of this is going to be 7 plus x. That's how we factor a difference of squares. It is what it is, right? If you don't believe me that this works, you could always double dip this through and you're going to see that it does actually give you 49 minus x squared. Anyway, on the bottom, this one's a little bit more traditional. Think about how we're going to factor this. Hopefully you can identify this is going to be a sum product rule question, right? It's just a normal standard form quadratic. We can just use the sum product rule to factor it. So we're looking for two numbers with a sum of negative 15, but a product of positive 56. Off the top of my head, oh, geez, this one actually I hadn't even thought of. I think what's going to work is negative 8 and negative 7. Yeah, as a matter of fact, I'll say that does work. So we'll have x minus 8 and x minus 7. Now, if you look at what we've got now, it doesn't look like anything cancels out. But just remember, that last slide, I told you guys about additive inverses. Go figure, there's actually one that uses it here. Notice we have 7 minus x on the top and x minus 7 on the bottom. Those actually do cancel out. It's just we need to replace one of them with a negative 1. So you know what? I'm going to cross out this one and I'll cross out this one. And just for fun, I'll put the negative 1 up on top. So I'll put a negative 1 up there. This is going to give us, you know what, I'll bring the negative 1 out in front so it doesn't look as lost. Negative 1 times 7 plus x over x minus 8. And you can put that in brackets if you want. You know what, maybe I will, just so it looks a little neater. And that's it. Nothing else is going to cancel here. If we were to double dip that negative 1 through, it's just going to change how it looks. It's not really going to do anything useful. So I would say that this is now fully simplified. However, we can't forget we have to list our NPVs, of course. The NPVs, the non-permissible values, those are the values that would make us divide by 0. So in other words, the values that would make your denominator equal to 0. Even the ones that get crossed out, you still have to consider it as an NPV. So we've got x minus 8 right here. The value of x that would make that equal to 0 would be x equals 8. The other one, x minus 7, you can write that as, of course, x equals 7, because if 7 was x, you'd have 7 minus 7, so you'd have 0 in the denominator. Those are your NPVs. Now it's up to you. I'm not sure if I would have explained this last class or not, but with your NPVs, you can say x equals 8 and x equals 7, or if you want to be like really correct, you could say x cannot equal 8 and x cannot equal 7. Honestly, I don't really have a preference, right? The fact that you're saying they're non-permissible values, even if you said equal, it makes sense in the first place, right? But anyway, those are your NPVs. Do whatever you want with it. Equals, not equals is up to you. I'll know what you mean, right? Anyway, let's look at this next one. Negative 6x plus 14 over 3x minus 7 squared. Interesting. All right, so we need to factor this in order to simplify it. At first glance, you might look at that numerator and go, hey, wait a minute, nothing factors there. Well, let's do the best we can, though. If you look at 6 and 14, a number that comes out of both of those would be 2. So why don't we factor a 2 out of that? So this is going to give us 2 times negative 3x plus 7. And then on the bottom there, 3x minus 7 squared. Well, that's going to be, that's just 3x minus 7 times 3x minus 7. Huh, okay, interesting. So right now I can see there's a 3x plus 7 on the top, a negative 3x plus 7 on the top, and we have just two 3x minus 7s on the bottom. This 3x plus 7 on the top here, this looks like I could do something with it to cancel out this 3x minus 7. The best thing I can think of is maybe we should also take this negative out of the brackets here, right? So in other words, let's take this negative and tack it onto the 2. Because it's coming out of the full set of brackets, we have to change the sign of both of these two terms here. So this is going to give us negative 2 times 3x minus 7, because again, that negative comes out of both of those there. So even out of the positive sign, you have to have a negative sign now. This is all over 3x minus 7 times 3x minus 7. Ooh, that's a miserable looking 3. Hold on. 3x minus 7. All right. Anyway, now what you hopefully notice is we have 3x minus 7 on both the top and the bottom. We can just knock those right out of the park. So this gives us negative 2 over 3x minus 7. Bingo, bango, bongo. We got it. That's our answer. Now we got to list our NPVs. Good news is if you look at our denominator, there's two of the same thing on the denominator. So in other words, our NPV is going to be the same for both of those chunks. Just set that equal to 0. And again, if you can do it in your head, great. If you can't do it in your head, it just helps maybe to go 3x minus 7 equals 0. Okay, we want to get x by itself, so let's add 7. Oh, and then we got to divide by 3. So long story short, we have x equals or cannot equal, whatever you want to say, 7 over 3. There it is, right? So again, moral of the story is to simplify, you have to factor the top and you have to factor the bottom, then cross out anything that looks the same. Listing the NPVs just means look at the denominator and figure out what values of x would make that equal to 0. Anyway, we got to move on. We got lots more to do here today. So the actual new thing today, multiplying rational expressions. Here's some good news. this is pretty much the exact same thing as multiplying regular fractions, which, in case you've forgotten, is just multiply the tops and multiply the bottoms. However, this time around, there's a new first step, right? So because we're actually dealing with rational expressions, with polynomials, we get a new first step. Here's the first step, though. Factor both the numerators and denominators. Big surprise, right? When we're dealing with rational expressions, like a polynomial over a polynomial, you always have to factor it. You can't start by doing anything other than factoring. I mean, you could, but it's going to make your life a lot more miserable. Just factor the whole thing, both the top and the bottom first. Then step 2, multiply numerators, multiply denominators, leave it in factored form. You don't have to multiply back through. Like literally, you don't have to do that. It'd make your life much more difficult if you multiplied it through. Just leave it in factored form. And here's why. Step 3, cancel any common factors from the numerator and denominator. So just like we did with simplifying, just cancel out any things that are the same on the top and the bottom. Step number 4, expand by multiplying the leftover factors. So in other words, clean up the top, clean up the bottom. Like I actually do want you to expand it out there. And then step number 5, list the NPVs present in any step. There could be a whole bunch when you're multiplying these rational expressions together. Anyway, let's do a few examples together. So first one, right off the bat here. This one's a little bit of a sneaky one. Every single year when I do this, I'm like, oh, why do I start with this one? Remember, the first step is factor everything. Well, these are just monomials, like one piece over monomials, like another one piece. Like everything's all multiplied together. In other words, it's already technically factored. So we don't actually have to factor anything here. We can just multiply straight across. Now, we could leave it quote unquote factored, but really there's nothing wrong with just saying, okay, 6 times 20, which is 120, and then x squared times x to the power of 3, which is x to the power of 5. And then we just have y to the power of 4. It's just going to chill there on its own. And then on the bottom, we have 5 times 9, that's 45. And then we have, well, x squared is just going to chill on its own. And then we have y times y3, well, that's y4. Next step, I guess, we could just cancel out anything that's, the same on the top and the bottom. First of all, we'll start with the variables. I think the variables are a little simpler. Y4 is just going to knock out with y4. And then for x5 and x squared, we can cancel out the x squared in the bottom, and it's going to drop this x5 down to x3. Again, that's just because when you have x to the power of 5 divided by x to the power of 2, you're dividing powers. That just means you have to subtract your exponents. Last one there, 120 over 45. I'm feeling pretty lazy. I don't know if I really want to try to simplify this, but we do have to simplify it. Think of it just as a normal fraction. I know one thing that's going to come out of it. There might be something better than this. We'll see in a second. But one thing that I know comes out of this for sure is 5. So if we divide both the top and the bottom by 5, I think this is, hold on, I'm just doing the math in my head. I think if you divide 120 by 5, I think you get 24. Yeah, I think you do. You get 24. I'm just thinking about that again. Yeah, it is. It's 24. So we have 24x3 over 45 divided by 5 is just 9. Oh, and then we can go further. Now I can divide by 3. Okay. Anyway, it is what it is. Anyway, so both 24 and 9, they both divide by 3. That's going to give me 8x to the power of 3 over 3. There it is, simplified. Right, so the whole point of this is this thing that I just boxed is literally equal to this whole chunk over here. They're the exact same expression. It's just this one is simplified. So obviously there's some use to this. It certainly cleans up these expressions quite nicely. Anyway, we do need to list our NPVs. So for our NPVs here, you look at anything that was ever in the denominator. Well, we had x and y in the denominator. There was no like plus or minus anything to it. So we know full well it's just going to be x cannot equal 0 and y cannot equal 0. Done. There's our NPVs. That one wasn't super exciting. So, those are not really typical. This next one, however, is certainly a lot more typical. X minus 3 over 5x plus 7 times this whole mess right here. All right, first things first, you got to factor everything. This rational expression on the left, this x minus 3 over 5x plus 7, that thing's already technically factored. So guess what? I'm just going to leave it as x minus 3 over 5x plus 7. And I know it's factored, especially like x minus 3 is pretty clear. 5x plus 7, nothing comes out of both of those. So I knew that was factored. Then this is going to be times this guy right here, 25x squared minus 49. I want you to think about how you'd factor that. Think about what kind of method you'd have to use when it's this minus this. Hopefully what you're thinking in your head right now, difference of squares, right? Both of these are square rootable, so square root each piece, right? So in other words, this is going to be 5x, that's the square root of this first piece, minus 7. And then remember, you have to multiply by the conjugate, so it'd be 5x plus 7. No big deal. This guy on the bottom, a little bit unusual, xy minus 3y. Well, something that comes out of both those terms would be y, right? So y can come out, and then that leaves us with x minus 3. So now what's really nice is you can multiply both of these straight across. Just leave it in factored form. Now here's something I do as a little trick. And some teachers would probably roll their heads at this and go, oh my goodness, what on earth are you doing? But instead of writing this again, where we just literally write everything all over again, just without the times between, right? We just, have everything on the top and everything on the bottom. What I usually literally do is I just go, okay, now that everything's factored, I just pretend this like multiply sign isn't here anymore. And then I kind of just pretend it's one jumbo fraction, right? Everything all together. Because when you're multiplying factors, they just stay outside of each other anyway, right? Whatever, right? So I use that as a time-saving measure and a paper-saving measure, let's be real here. But you can do whatever you wish. Anyway, so now we've multiplied this together. It's one jumbo fraction. Now we can cross out anything that's the same on both the top and the bottom. Well, first things first, I notice I have x minus 3. Those are now gone. I also have 5x plus 7. Those are now gone. So the only thing left is 5x minus 7 over y. And there's no expanding to do there because everything else is gone. So guess what? That's our final answer. That's it, right? Not really a lot different than simplifying, right? So it's just this added step of multiplying them together. And really that just means once you have it factored, you just, draw it as a single fraction. Anyway, we need our NPVs before we forget. Remember, the NPVs are anything that ever shows up in the denominator. So literally any of those three pieces right there, even though they canceled out, you have to still consider them an NPV. First of all, the obvious one, y cannot equal 0. That one's pretty easy. Then I think the next simplest one would probably be this x minus 3. That means x cannot equal positive 3. The last one here, 5x plus 7. Again, that might be a little bit more tricky for some of us. So you can write just separately here. You can say 5x plus 7 equals 0. Minus 7 over, this gives us negative 7. Then divide by 5. So x is negative 7 over 5. I'll write that over here. X cannot equal negative 7 over 5. There it is. All right. So there's our NPVs. We've listed them. We're good to go. That's it for multiplying. That's really all there is to it. Now, I think we'll do some more examples. Yeah, here's another example. This one looks like a beefcake. Let's test this one out as best we can. No promises on this one. So again, before we begin, we need to start by factoring every single piece of this. Look at the numerator over here. This technically is already factored. It's just a monomial. Everything's all stuck together already. So we'll just write that as 6m cubed n. That's all we can do there. On the bottom, think about how we'll factor this guy, m squared minus 4m. Now you might be thinking in the back of your mind, oh, it's a difference of squares. Not really. This m right here, it's ruining everything for us, right? We can't do a difference of squares there. So instead, what we're going to do is notice we could factor an m out of both of those pieces. This is kind of a sneaky one, right? So m times, if we factor an m out of both of these, it'll be m minus 4. That's now all factored, so we're good to go. Now let's look at the numerator over here, m squared minus 16. That one is a difference of squares. So why don't we just go m minus 4, so remember the square root of each piece, times m plus 4. Then last one here, think about what we could factor out of both of these. I see I could factor a 4 out of both of those. And we could also factor an n out of both of those. So we'll do it all at once. We'll just say 4n times, if I factor out a 4n from this, I'm just left with m, plus, if I take 4n out of this, I'm just left with plus 4. Okay, so that's all factored. That was quite a crunch right there. Remember, once you have it factored, you can just do that trick where I just say, you know what, just ignore the times, make it one big fraction. Just for fun, I'll put this in brackets so it's not totally weird there. Now we start thinking about what can cancel. One thing I see right off the bat, m minus 4, that can go. M plus 4, that can go. There's a loose m right down here. See the m right here? We can cancel the loose m out with one of these m's right here, so that knocks it down to m squared. There's an n right here that'll cancel out this n. And then if I clean this up and rewrite what we've just got left, there's not really all that much. We have 6m squared over 4. Well, 6 over 4, that can simplify down as well. You could divide both those pieces by 2, and just like simplifying a normal fraction, that 2 just disappears. So this becomes 3m squared over 2. And that's it. That's all there is on that one. Of course, we have to list our NPVs. This one's going to be a gong show. Look at this. First of all, that was an m right there. So we'll say m cannot equal 0. And then for the m minus 4, we have to say m cannot equal positive 4. Then we had an n down here, so n can't equal 0. And then we had m plus 4, so that means m cannot equal negative 4. Okay, hopefully this is making some sort of sense. Again, you just have to factor every single piece here. The hardest part, as far as most people are concerned, I think, is just figuring out what factoring strategy to use. Again, I've done this a million times, so if I'm going pretty quick, that's why. Don't expect yourself to have to go that quick, but it is what it is. Anyway, let's get moving. Here's another example. Oh my goodness, this one looks like an absolute train wreck. All right, here we go. So think about what can factor out of the top up here, 2xy plus 7y. Is there anything that factors out of there? I think the only thing I can see is y. So y times 2x plus 7. That's about as good as we're going to get there. Then on the bottom, this is a classic sum product rule. We're looking for two numbers with a sum of 10 and a product of 21. So a sum of 10, product of 21, that would be 7 and 3. So it's going to be x plus 7 times x plus 3. I don't need this line to be that big. Let me just go like that now. Perfect. Now times this other side, 9 minus x squared. Notice this is a difference. Both of those things are square rootable. So again, that's a difference of squares. We can say that's 3 minus x times 3 plus x. Oh, what on earth am I doing? 3 plus x. There we go. And then on the bottom here, that was a horrible line. Let's try that again. On the bottom here, 2x squared plus x minus 21. I got bad news for us. This is an adapted sum product rule factoring question. It's been a while since we've done one of these, so I'm going to kind of lay you through this one. So we got 2x squared plus x minus 21. The sum is still the same. We're looking for two numbers with a sum of technically plus 1. And we're looking for two numbers with a product, this time of 2 times negative 21, which is negative 42. So you need to think of two numbers that add together to equal positive 1, but multiply together to give you negative 42. Now, before I tell you what those answers are, I want you to remember when you have a negative product, that actually tells you that one of your numbers is positive and one of your numbers is negative. That's the only way you can get a negative product. I guess what the two answers would be is positive 7 and negative 6. Positive 7 times negative 6 gives you negative 42. Positive 7 plus negative 6 equals positive 1. Now, here's the bad news, though. You can't just jump right to the factored form with this. There's a little bit of work we have to do with these two numbers. We have to use these numbers to split apart the middle term. Yeah, this was really fun. So if we split apart the middle term here, we're going to have 2x squared plus 7x minus 6x minus 21. So again, I use 7 and negative 6 to split apart that middle term right there. Then you put brackets around the first two and brackets around the second two. But be really careful here. Notice I have a minus sign in between. As soon as I draw those brackets between these two, this minus sign needs to change this sign over here from a minus to a plus. If it was already a plus sign, it would have to change it to a minus sign instead. The nice thing about that is if you missed doing that, like if you didn't catch that step, in the next step, you would see why that was so needed. The next step is we have to factor whatever we can out of each of these pairs of brackets. The only thing I can see coming out of the first one here is just an x. So we have x times 2x plus 7 minus, the only thing I can think of coming out of these two is 3. So we'd have minus 3 times x, 2x plus 7. And here's what I mean in that if you hadn't changed that to a plus sign, you would have caught it in this step. Notice we have 2x plus 7 and 2x plus 7. Because those match, that tells us that we've done this correctly. So our two factors here are 2x plus 7 and x minus 3. So again, we can write this over here back to our rational expression, 2x plus 7 times x minus 3. Finally, this thing is now all fully factored. You can do the thing where you just erase this time sign and write it as a single fraction. Now think about anything that can cancel out here. X plus 3 and 3 plus x, those are the exact same thing with addition. Order does not matter. So 3 plus x and x plus 3, those can cancel out. We have 2x plus 7 and 2x plus 7. Those are gone. And then we notice, sorry, that we have 3 minus x and x minus 3. Those are additive inverses. Remember, so when you have subtraction and then they're reversed, like 3 minus x and then x minus 3, those can actually cancel out. You just have to replace it with a -1. Again, that only happens with subtraction. With addition, 3 plus x and x plus 3, you don't have to do it because those are already the same thing. With addition, order does not matter how you add or add them together. It's only with subtraction that the order matters. That canceled pretty much most of this out. I'm just going to use this -1 on the y now. So I have -y over x plus 7. And that is as simple as that's going to get. And that's actually kind of remarkable when you think about it. If you look at what we started with, this huge chunk right up here, this huge chunk is literally just equal to -y over x plus 7. So obviously it's much, much simpler. If we can actually simplify things down, it really cleans it up for us. Anyway, we need to list our NPVs. Even if it doesn't ask, you still have to list them. Look at the fully factored form. It kind of tells the whole story for you. We have x cannot equal -7 for this first piece. X cannot equal -3 for that second piece. For 2x plus 7, you could write it out again. I'll save us the trouble. I'm going to say x cannot equal -7 over 2. And then for x minus 3, we have x cannot equal +3. So notice a whole bunch of NPVs. That's pretty normal on these ones. Not a huge surprise. All right, last thing we got to do today, as if that wasn't already enough. This is a long lesson. I apologize, guys, but we're almost done. We're almost done. The last thing we have to do today is dividing rational expressions. Now, I could probably just hear your groan right through the screen right there. You're probably like, oh, geez, are you kidding me right now? Now we got to divide these. Slow your horses. These are actually not that bad. I want you to remember that when you divide fractions, just like in this picture here, right? So let's say we had a over b divided by c over d. When you divide fractions, you just keep the first one. So the first one stayed the same. You change the divide sign to a times, and you flip the second one. So instead of divide by c over d, you're just going to times by d over c. This is just keep, change, flip, right? This is something you would have hopefully done back in Math 8 or Math 9. But here it is again now in Math 20-1. So again, when you divide rational expressions, I want you to start by factoring the numerators and denominators. Then after you factor it, you need to take the reciprocal of the second fraction and then you multiply them as normal. So this is just multiplication with literally one extra step. Now here's a bit of a warning. Keep in mind that since you have like a division and then a flip kind of thing, there's going to be a lot more NPVs when you're dividing rational expressions. Like I kid you not, it's not unusual for you to have upwards of 6 different NPVs. Not always, sometimes you have fewer than that, but just keep in mind, there's going to be a lot of NPVs because NPVs are things that show up in the denominator at any step, even before you flipped, right? And after you flipped, right? So these NPVs are going to show up everywhere. Anyway, let's see an example. This first example, not too crazy. It's just a bunch of monomials in here. So in other words, this thing is already all factored. Basically, we just have to start by keep, change, flip, right? Since it's already factored, we don't have to worry about it. So what this becomes is -4t squared over 16x squared times by the reciprocal of this. So 4x over 8, ooh, that's an ugly 8, 8t squared. Might as well multiply it together now. -4 times -4, that's -16. And that would be xt squared over 16 times 8. Hold on, I got to grab a calculator for that one. I'm too tired to do that right now. So 16 times 8, 128. And that's going to be x squared t squared. And then anyway, we got 16 over 128. That should factor down to 1 over 8, I believe, because I'm pretty sure 128 is divisible by 16. Anyway, long story short, that's -1 over 8. The x cancels out with one of the x's in the bottom, and both these t squareds are gone. This just leaves us with -1 over 8x. Whew, that was quite the hustle right there. If we look at this whole thing, of course, we need to, of course, list our NPVs still. So NPVs. Remember, NPVs just show up, you know, no matter where, like in any part of your denominator is what I'm trying to say, right? So anywhere that something showed up in the denominator, there is going to be an NPV there. So long story short, let's look at what we started with. We had x on the bottom on both of these, so we have to say x cannot equal 0. Then we have, I guess we have t on the bottom over here, so then we have to say t cannot equal 0. And actually, I think that's about it. I don't see anything else appearing in any of our denominators that would give us any issues. So those would be our NPVs. Wow. Okay. Don't know how many more questions we have here. You know what? I'm just going to double check. It says tough example. Oh, look at that. The end is in sight. The end is in sight. My goodness. Tough example. It says it's not so tough. We're tougher than this one. I'll show you something. Anyway, so we got to do this quote unquote tough example here. This is a division of rational expressions. We have to always start by factoring the whole thing first. Let's look at the top left one. X squared minus 13x plus 36. I want you to think about what method we're going to use to factor this. It's a standard form quadratic, so we're going to be using the sum product rule. So we're looking for two numbers with a sum of negative 13, but a product of positive 36. Think about that for a second. Sum of negative 13, product of positive 36. It always helps just to think of the product and then see if it gives you a sum. It's a negative sum, so we have to have two negative numbers. It's going to be negative 9 and negative 4. So we have x minus 9, x minus 4. Over, look at this bottom one, x squared minus 9x plus 20. Once again, a sum product rule question. We're looking for two numbers with a sum of negative 9, but a product of positive 20. Focus on that product. What two numbers multiply together to give you 20? But then they'd add together to give you negative 9. Hopefully the answers you got are negative 4 and negative 5, right? Anyway, divided by. We're not keep change flipping yet. We have to keep it divided by, right? X squared minus 81. That is like a classic example of a sum product rule right there. So that's going to be x minus 9, x plus 9. Cool. On the bottom, once again, x squared minus 25. Another classic example of a sum product rule question. So that's going to be x, or sorry, not sum product rule, difference of squares. Hope I said difference of squares the other one. Geez Louise, you can tell I'm getting tired. Anyway, x minus 5, x plus 5. Whew, there it is. All right, now that we have everything all factored, this is useful. We now need to turn it to a keep change flip. So in other words, keep the first fraction the same, x minus 9, x minus 4, over x minus 4, x minus 5, times the flip of the other one, x minus 5, x plus 5, over x minus 9, x plus 9. You could have canceled some of these things out in the first place. I, generally speaking, don't recommend you to. I think it's better just to have it all as one piece. Anyway, long story short, now we have everything factored. It's a multiplication of two different rational expressions. Guess what? We can just ignore that time sign, think of it as one jumbo rational expression, and then go cancel out anything that shows up on both the top and the bottom. The one thing I see is x minus 9 and x minus 9. That's all well and good. X minus 4, x minus 4, x minus 5, x minus 5. What do you know? This whole thing is just x plus 5 over x plus 9. That's it. There's nothing else to it, right? So this tough example, this huge, big, chunky piece, just simplifies straight down to that. To wrap this up, though, as if that wasn't enough, we have to list our NPVs, and there are a whole bunch in this example. Let's start by looking at the first time we factored something here. So in this part right over here, we have x cannot equal positive 4, x cannot equal positive 5, x cannot equal, that'd be a positive 5 again. So guess what? We don't have to write it a second time. This time it's going to be x cannot equal negative 5 because of this x plus 5 here. And then we also have to consider the ones that showed up in the denominator after we keep change flipped it. That was just these two right over here. So we also have x cannot equal positive 9 and x cannot equal negative 9. So a whopping 5 different NPVs here. That's a whole ton of them, but it is what it is. We had to list all of them. Wow. Okay, so that was an extremely long lesson. I apologize. Hopefully it didn't go completely over your head. And if it did, hey, well, the answer key to this this lesson is, of course, posted on Google Classroom. What I need you to do for some practice, there's not a lot of questions listed there. Just page 327, questions 1, 2, 8, 10, and 11. Give those ones a shot. Practice is absolutely key here. Again, the hardest part, I think, is just figuring out how to factor certain different things. Sometimes even just the sum product rule ones can sometimes stump us if we have a hard time thinking about what adds together and multiplies together to give you some numbers. Anyway, best of luck here. I'll see you tomorrow.